Okay, we're back for our final lesson, binomial theorem. So this is a bit of a long one, so let's get going here. All right, binomial theorem. When I have a binomial raised to the exponent of n, it follows this pattern. nc0 x to the n plus nc1 x to the n minus 1y plus and on and on. These values, the coefficients in particular, follow Pascal's triangle. But we're not going to rely on Pascal's triangle. We're not going to have a picture of it with the numbers filled in and use those coefficients to fill it in. We're actually going to use combinations, and the work we did yesterday in that part of the lesson, building up to this, will help us to establish what the coefficients are and then the patterns with the x's and y's as you expand the binomial. Okay, this part I'll leave till example 2. Okay, we'll get to that one, but let's do one of the basic binomial theorem applications where we expand a binomial. So this time we don't have just something neatly as x and y, right? So if we think of it this way, right, let's start stating all the key values. N equals 5, so that means we have six terms. Okay, now x is equal to 3a, and y is equal to negative 4b. Now when we expand these, we're going to have to plug these values in. Okay, so the first term, so I'm going to clean this up a bit here before we get going. Okay, our first term, so I'm going to build this using the binomial theorem. First term is nc0 x to the n. So that is n is 5c0. My x value, instead of x, I'm going to put 3a, and my n value is 5. There's my first term. Plus nc1 x to the n minus 1y. Okay, so plus 5c1. My x value is 3a to the 5 minus 1. And my y value is negative 4b. Okay, and then the pattern's just going to keep going. So let's finish the pattern. So 5c2, 3a to the 5 minus 2, negative 4b squared, plus 5c3, 3a to the 5 minus 3, negative 4b to the third, couple more to go, plus 5c4, 3a to the 5 minus 4, times negative 4b to the fourth, and then plus 5c5, 3a to the 5 minus 5, and negative 4b to the fifth. Okay, you can use your calculator to simplify all these combination values, so let's simplify that. So that's 1 times 243 a to the fifth plus 5 times 81a to the fourth negative 4b plus 10 times 27a cubed 16b squared plus 10 times 9a squared negative 64b cubed plus 5 times 3a times 256 b to the fourth, and the last term plus 1 times negative 1024 b to the fourth. Okay, let's clean all of that up. So you notice here, I'm just going to pause and just show you real quick. Coefficients, right? Pascal's triangle. 1, 5, 10, 10, 5, 1. If you check the 6th row Pascal's triangle, you'll see that those are the coefficients indeed. Okay, let's continue. Okay, cleaning all this up. Let's multiply everything out. 243a to the 5th plus, 243a to the 5th minus 1620 a to the 4th b plus 4320 a to the 3rd b squared minus 5760 a squared b cubed plus 3840 ab to the 4th minus 1024 b to the 5th. Whew. So there is our expansion of 3a minus 4b to the 5th. Okay, that's one useful tool, or the one useful thing with our binomial theorem is to expand something out. Imagine trying to do that by hand. Remember doing that in Math 10C and 20-1? It takes a long time to multiply it out by hand. This binomial theorem makes it much easier to do. Okay, example 2. Algebraically determine the third term in the expansion of 5m squared plus 2 to the 6th. So you can't be multiplying everything out. You can't be using the binomial theorem to do the entire expansion, then pick out the third term. I want you to show me algebraically. Okay, so first let's look at the key parts of 5m squared plus 2 to the 6th. So that is n equals 6. I have 7 terms. My x value is 5m squared. My y value is 2. Okay, here's the key thing here. So term, third term. I'm going to go back up here. We're going to use this formula, each term. So we're not looking for the entire expansion. We just want a single term, right? In general, the single term is given by the formula t sub k plus 1 equals the combination of n things taken k at a time multiplied with x to the n minus k multiplied with y to the k. Important note here is that k plus 1, that is the term number, not k. So if I go all the way back down here, k plus 1 is the term number. Well, literally, k plus 1 equals a term number. We're looking for the third term. Okay, so k plus 1 equals 3. So solve for k equals 2. This is an important value to keep in mind. K equals 2. This is like your R value that we talked about in the previous lesson. Okay, so now that we have all of these, let's rewrite the formula for a particular term of a binomial expansion. Okay, follow this formula. Okay, t to the k plus 1, well, that is just t to the 3. So t to the 2 plus 1 equals, the n value is 6, combination, taken how many k times? So 2 times. X, well, we're not going to put x, we're going to put 5m squared. So that's my x value here. Oops, 5m squared to the exponent n minus k. That's 6 minus 2 times y, which is 2, and then raised to the k exponent. Okay, so t to the 3. So we're looking for third term. Combination of 6 things taken 2 at a time. That is 15 times 5m squared to the 4th, and that's 2 squared. Okay, simplifying, 5m squared to the 4th is 625 m to the 8th times 4. So my third term is 37,500 m to the 8th. Okay, example 3. In the expansion, whoa, okay, look at this binomial. X cubed minus 2 over x raised to exponent 7. Algebraically determine which term in simplified form contains x to the 5th. Okay, so again, we're not going to multiply all this out. We're not going to do the full binomial expansion and then find the term that has x to the 5th. We want to do this algebraically. Okay, so let's get some key facts down. N equals 7. Okay, x is x cubed, and then y is negative 2 over x. Okay, which term? So we need to find what k equals and ultimately what k plus 1 equals, right? Because this is your term number, right? But let's find k first. So let's think about our formula, okay? T to the k plus 1 equals nck x to the n minus k y to the k. Let's start plugging everything in. I'm going to leave tk plus 1 as is. That's what we're solving for. Okay. N is 7. C, and then k is unknown, so I'll leave it as is. X is x cubed. N minus k, well, that's 7 minus k. And then y is negative 2 over x. And then the k value is just k. We don't know what that is yet. Okay. Let's do a little bit of simplifying and rearranging. So 7ck, so that's x to the 21. Let me use the power rule here for exponents. And then let me do this, negative 2 x to the negative 1 to the k. Okay, let's simplify this a bit more. I'm going to do this, negative 2 to the k. I'm going to distribute that exponent, so negative 2 to the k, and then x to the negative k. Okay, this will make my simplification a bit easier. Okay. Okay, we're getting there. Okay, here we go. Let's combine the two x terms. So remember, product rule, we add the exponents when the bases are the same. So I have an x and an x base. I'm going to combine that base. 21 minus, when I combine the exponents, is 21 minus 4k. And what am I left with? Negative 2 to the k. Okay, let's look back. Contains the x to the 5th term. Well, that's going to be a constant. That's going to be a constant. So constant, constant. This is your variable term. Okay, so x to the 21 minus 4k must equal x to the 5th. We have the same base, so we can just set the exponents equal to each other and solve for 5. Okay, so I have negative 4k equals negative 16, and k equals 4. Okay, so back to here, if k equals 4, k plus 1 equals 4 plus 1, k plus 1 equals 5. Remember we said k plus 1 is your term number. So we are talking about term 5. So term 5 has the x to the fifth. Okay, next page. Okay, applying the binomial theorem where k is unknown. So one term in the expansion of x plus a to the 11th is negative 4,455 x to the 8th. Algebraically determine the value of a. Okay. I'm not given the term number. So how are we going to do this? Let's write down what we know. N equals 11. X is just x. My y is a. Okay, let us write our formula for the particular term in general. Okay, and let's start plugging stuff in. So t to the k plus 1, n is 11, I don't know k. I have x to the 11 minus k, and then this is a to the k. Okay, we just have variables of x's here, so it says one term in the expansion contains, so this is the key here, contains negative 4,455 x to the 8th. So that's our key piece of information here. So what am I going to do with that? Okay. This is a constant. This is a constant. Okay, this is my variable, right? So x to the 11 minus k. Whatever this term is, I don't know the term number, but I know that this x to the 11 minus k, it must equal x to the 8th. So the bases are the same. I'm going to set the exponents equal to each other. K equals 3. Okay. Now that k equals 3, k plus 1 equals 4. We're talking about the fourth term. Okay, we're not done yet. We still need to find the value of a. So I'm going to take this equation. Okay. Now I'm going to plug in my k value. 3 plus 1, 11c3, x to the 11 minus 3, a to the 3. Okay, so the fourth term, 11c3, is 165, x to the 8th, a to the 3rd. Okay, how do we solve this? We know the fourth term. This is the fourth term right here, fourth term. So I'm going to set it equal to the fourth term. Negative 4,455 x to the 8th equals 165 x to the 8th, a to the 3rd. Okay, x to the 8th cancels. I have negative 4,455 equals 165 a to the 3rd. Divide both sides by 165. I get negative 27 equals a to the 3rd. Take the cube root of both sides. I have negative 3 equals a. That's my a value. Okay, example 2. Algebraically determine the constant term in the expansion of 2x plus 1 over x cubed to the 8th. So the constant term is the term without a variable. Let's think about it this way. First term, without even using the formula, let's reason this out. Okay, first term will have x to the 8th. Not worry about what the coefficients are, right? Because the coefficients are not going to affect whether we have a constant term or not. It's the exponents, right? Because when I'm multiplying this term with this term, in the umpteen ways that we multiply it throughout the binomial expansion, somewhere along the line, we're going to get, this is a negative exponent here, this is a positive exponent. Somewhere they're going to cancel where it's going to be 1, and then we're going to have a constant term, right? So if we logically think first term will have an x to the 8th, what about the second term when we multiply everything out, right? The second term we know will have to step down. So if the first term has x to the 8th, second term has an x to the 7th. Again, not worrying about what the coefficients are. The second term for the y value will have 1 over x to the 3rd to exponent 1. So that's x to the 4th. What about the third term? X to the 6th, 1 over x to the 3rd, right? Remember, the values go up for the y value, so it's going to be 2. Well, bingo, that's equal to 1. No more exponents, right? So the third term will have the constant. Okay, and then if you encounter a problem that says, okay, great, the third term has the constant, well, what is the third term? So let's figure out the third term. Let's do that just for fun. Okay, n equals 8, x is equal to 2x, y is equal to 1 over x to the 3rd, k plus 1 equals 3, third term, so k, solving for k equals 2. Here's my formula. T to the 2 plus 1 equals, n is 8, c, and then k is 2, x is 2x, n minus k, 8 minus 2, and then the y value is 1 over x to the 3rd, and then the k value is 2. Third term, 8c2 is 28 times 2x to the 6th, 1 over x to the 6th, 28 times 64 x to the 6th times 1 over x to the 6th, 28. So the x to the 6th divide out to 1. So I'm left with 28 times 64. The third term is 1,792. Okay, that's if I asked you to find the actual third term. Okay, but we identified that the third term is the one with the constant. Okay, last part of the binomial theorem, application, Pascal's triangle, and pathway. So we can actually use Pascal's triangle to help us determine like the possible number of pathways. It's actually kind of cool how this works out in a grid. Okay, so let's take a look at this grid here. This is very familiar. This is Pascal's triangle. If we overlay a grid, we'll see that it's like our rectangular grid city problem, where if I wanted to get from point A to B, how many different ways would it take? Well, 10. And we can also see that same Pascal's triangle, except written in combination form. If I overlay the same grid, well, that number corresponds to that one. That's still 10. Okay. As shown in the second diagram, the answer 10 is equivalent to 5c3, which can be written as such. Okay. Let's do an example. Determine the number of pathways from A to B if you may only travel closer to B from A. Okay. So I'm just going to zoom in a little bit so we can see this a little bit better. I can write bigger. Okay, will that fit? Okay. We're going to solve this two ways. Solve using Pascal's triangle, and then it's asking, can you use permutations to solve the problems as well? We'll find out. Let's do the first part here. Okay, if I'm drawing on Pascal's triangle, right? Imagine this. It'd be easier if you can tilt it, but just think about it this way. Start with a series of ones, right? We know that Pascal's triangle starts with a 1 on the top. Well, how do we get, for Pascal's triangle, we are adding on the diagonal, right? The diagonal here is not visible, right? So imagine a square here. What's this value here, right here? It's not 1, it's 0. There's nothing there. So 1 plus 0 is 1. That's how you get this side value here is 1. If you carry on the same kind of analogy here, the number is 0, 1 plus 0 is 1. So all these values along the edges where there's no other number to add it to, it's just 1. Okay, so same thing. Let me just make this look a little bit neater. So all these 1s are here. We understand where those come from. What about this one? Same deal. Remember I said imagine a 0 out here. There's a little invisible rectangle. 1 plus 0 is 1. Same thing here. 0 out here. 1 plus 0. So 1 plus 0 is 1. We're adding on the diagonal. 1 plus 0 is 1. So if I just clean it up here, all the edges, right, they'll have the same number unless there's something on the diagonal to add it to. So this on the diagonal, 1 plus 1 is 2. So that intersection is 2. Okay, so you get the idea. I'm going to stop drawing those numbers. 1 and 2, that's 3. 1 and 3, oh, let me finish this row. 2 and 1 is 3. 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. Okay, 1 and 4 is 5. 4 and 6 is 10. 6 and 4 is 10. Okay, let's keep going until we run out here. 5 and 10 is 15. 10 and 10 is 20. 15 and 20 is 35. Uh-oh. I have 35 here. What's this number? Well, use that same analogy as before. Imagine an imaginary square here. There's a 0 here because there's no number, right? What's 35 and 0? That's 35. Okay, so same logic on this side. This would be 35. Okay, continuing. 35. 35. Okay, so that's 70. 70 and 35, 105. 35 and 70, 105. 105, 105 is 210. Okay, to go from A to B, there are 210 possible paths. The other question it asks is, can you solve this using permutations? Well, let's call this point X. So A to X, we have to go 1, 2, 3, 4 down, 1, 2, 3 right. So D, 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 R, R, R. Remember this from our permutations problem. There are 7 steps to get from A to X. So that's 7 factorial, but I don't want to repeat the D's and the R's. So 4 factorial, 3 factorial. So this is a permutations with repetitions problem. Okay, when I go from X to B, 1, 2 down, so D, D, and then 2 right, R, R. So that is a total of 4 steps, and I want to divide up the repetitions. So I'm going to multiply the 2 for all the possible paths. And look at that. What do we get? 210 steps. Or sorry, 210 possible paths. It's the same answer we get when we do the steps through Pascal's. Okay, let's do the next one. This one we have overlapping rectangles. Okay, we're going from point A to point B. Okay, I'm going to set up my Pascal's triangle numbers. The edges all have 1 to start, and then let's do that adding thing. So there's 2 there, 3, 3, 4, 6, 4, 10, 10, 5, that's 15, 20. Okay, what's this number, right? Imagine a 0 out here. 10 and 0 is 10, so that's just 10. Okay, the edge is going to keep being 10. This one, the edge is 15. Imagine a 0 out here. 15 and 0 is 15. Okay, let's keep going. 30, 35. This will be 50, 65, 40. This is 105. This is 115. And then this is 220. 220 possible paths. Okay, and this is just basically all we're doing is overlaying coefficients of Pascal's triangle. And once we get to point B, we have 220 possible paths. Here's a note for overlapping rectangles. Cannot use permutations formula. Must use Pascal's triangle. Okay, the problem is in this part right here. I'll let you explore, but the problem is in this overlap region right here, right? Sometimes I can go 1, 2, 3, 4, 5 steps. Sometimes I can go 1, 2, 3, 4 steps right. Okay, it's not always consistent. Okay, so that's the problem. So if you start from A, you can have all these different pathways, and you lose consistency when there's an overlap versus when it conveniently stops at a point, then it expands again.